for many decades, actually looked to find short flashes of radio light. But the problem compared to gamma rays, where we have gamma ray bursts happening a couple times a week over the whole sky, at least the ones that we can observe, the problem in radio is having sufficient sensitivity and field of view is quite challenging. So a telescope like the Parkes telescope, which is the current record holder in terms of finding large numbers of fast radio bursts, has found a couple dozen events so far. That telescope has sufficient sensitivity to detect this fast radio burst phenomena, which I'll describe in a few minutes, but it has an absolutely tiny field of view compared to that of an all-sky monitor. In fact, the Parkes telescope, even though it has quite a large field of view compared to your typical radio telescope, is still much, much smaller than a square degree. That means that even Parkes, which is very good at finding fast radio bursts, it still takes Parkes 10 days of continuous observing to find roughly one fast radio burst. So we're really not in the regime where we can do a radio all-sky monitor yet. The other challenge compared to high energies, X-rays and gamma rays, is the fact that radio signals are unavoidably corrupted or influenced by their propagation towards us. So the equation that you see at the top is trying to show you that the emitted signal, this S of t there, that comes from an astrophysical object is quite different than what we actually observe at a radio telescope. Because this signal is modulated by refractive and diffractive scintillation. It's passing through a transfer function describing the dispersive properties of the interstellar medium, Faraday rotation due to the line of sight magnetic field, scattering due to inhomogeneities along the line of sight due to multipath propagation. And thus what we detect has been corrupted by all of these effects. And on the right, for instance, this is showing you something that you should, if you're going to take anything away from this talk, understand very well, is that short duration radio signals are dispersed by the intervening ionized material. So what you're seeing as a function of frequency at time, some particular pulse will arrive later at lower frequencies. So certainly keep that in mind. That's critical to understanding most of the talk. So this is a hindrance. It makes it difficult to detect these types of signals, but it can also be a help because it helps us differentiate short duration radio flashes that are astrophysical in nature from those that are man-made from radio frequency interference. And it also allows us to, in some cases, learn more about what's going on along the line of sight and to use these effects as a proxy for distance as well, which is another crucial thing to understand. So 10 years ago, this conference is to a certain degree celebrating 50 years of neutron stars, but we're also celebrating about 10 years of fast radio bursts because 10 years ago, using the Parkes radio telescope, Dunk Lorimer and one of his students and a number of other collaborators, they found what is now colloquially termed the Lorimer Burst. And what is the Lorimer Burst? Well, the Lorimer Burst was a bright, non-repeating, single flash of radio light. It was detected off-axis, but it was still very bright. The inferred flux density is on the order of tens of Janskys. And as I just told you, the signal, because of propagation through the ionized material between us and the source, it is arriving later at lower frequencies. So in this frequency time diagram, again, the signal is arriving later at lower frequencies. And if you correct for this effect, if you, what we call de-disperse the data, so if you can imagine shifting all of these frequency channels in time such that they all line up at the same time, then that pulse that you see in the inset, that would be the pulse if you add all of the frequencies together. So this was interesting because this is a very bright flash of radio light. Given the field of view, which again is tiny for a radio telescope, the implied rate is hundreds of, or if not thousands of these events per sky per day. So if you had a radio telescope of comparable sensitivity to Parkes, and if you were looking at the whole sky, we would have found many fast radio bursts already during the time of this talk. And I told you that dispersion allows us to figure out kind of the distance to a source. So the amount of delay as a function of frequency is a proxy for distance, but you need another input, and that's of course how the material along the line of sight is distributed. So these two plots here are showing ISO contours, so constant dispersion measure, the amount of column density, let's say, along the line of sight, either looking down on our galactic plane in the left-hand side here, or looking on the right across the galactic plane. And you can see, of course, if you look within the plane of our galaxy, you build up material very quickly. There's lots of stuff to look through. And if you look off the galactic plane, then you don't build up a column density of dispersive material very quickly. So using a model like this, and the measured dispersive delay, you can figure out the distance to a source in a model-dependent way, of course. And what was interesting about the Lorimer burst was, well, we can figure out for this particular line of sight, which happens to be towards the Large Magellanic Cloud, we can figure out how much dispersive delay we would expect from all of the material from the Milky Way galaxy. And the amount of dispersive delay across the whole band is given by this green bar here. And as you can see, the amount of dispersive delay that was observed, much, much larger. So what Dunk Lorimer and his co-authors concluded was that this extra dispersive delay must come from another column of ionized material, from the intergalactic medium, and potentially from the host galaxy of this source. So they concluded that this must be an extragalactic radio signal that had traveled through the ionized material of its host galaxy and through the ionized intergalactic medium. So this is very interesting because not only was this source bright if it was at that kind of distance, and we're talking about a distance of 1.5 gigaparsecs or so, it would have to be quite unlike radio signals that we see from typical pulsars. And this means that we're then probing a new parameter space of radio transients. This is a diagram that was made by Evan Keane, but it's based off work that Jim Cordes pioneered in the early 2000s. Essentially what it's showing are various different types of radio transients as a function of their duration. The x-axis is basically the duration of the radio transient, and then its luminosity on the y-axis. And pulsars, they inhabit this area around a few milliseconds or so with typical luminosities of a few Janskis per kiloparsec squared. We have the crab giant pulses over there at much shorter durations and much higher luminosities. But the Lorimer burst, as you can see, is many orders of magnitude higher in luminosity if the inferred distance is correct. And of course, as many of you know, there was a great deal of controversy about the extragalactic interpretation because that was based purely off this unexpectedly large dispersive delay. So that's really interesting. Apparently we have this new type of phenomena, this fast radio burst phenomenon. They appear to be coming from extragalactic space. They are very, very bright, short duration. Many, many models have been published speculating on what these sources might be. There have been galactic models in the early days trying to interpret these things as pulsars or magnetars, perhaps behind some extra cloud of ionized material that we had not previously known about. But there's also many extragalactic models, some of which are very exotic in variety, even evaporating black holes. So what are these sources? We don't know yet, but this is one of the things I'm going to try and touch on in the talk. And let's assume that they are real and that they're extragalactic. What good are they to us? What can they teach us? Well, they're certainly, if they are extragalactic, they're certainly the sites of extreme energy densities. So they're, I think, important in their own right to understand what kind of extreme astrophysical environment can produce such bursts. They may be pointing us to a new type of astrophysical object, although for the purposes of this conference, hopefully they're pointing us towards neutron stars, otherwise I'm speaking at the wrong conference. But regardless of their nature, if we can understand some of the complicating factors at the site of production, the influence of the host galaxy and other messiness, potentially they could be very interesting probes of intergalactic space, because again, the signal that we're observing has been modulated in various ways because of its propagation through the ionized intergalactic material. So we could use these sources potentially to probe the densities and the magnetic fields of intergalactic space in a way that's not possible otherwise. So just to give some context to what I'm going to be talking about here, basically the history of the field in the last 10 years or so is that we started with this Lorimer burst, the first, let's call it fast radio burst. There were actually a number of interesting papers written in the last few decades that in retrospect may have actually been detecting this phenomena as well. But between the Lorimer burst and really the field getting going, amount of time passed in which there was a lot of let's say, controversy about whether the sources were even astrophysical in nature. And as many of you know, for instance, at Parkes they discovered a somewhat similar phenomena that was coming from opening the microwave too early during lunchtime. And these kinds of things really, stopped the field from gaining a large amount of momentum in the early days. But really, with the discovery of a whole population in 2013 by Thornton et al., they found 4 fast radio bursts in a survey with the Parkes telescope. I think a lot of people really started to believe that this must be an astrophysical phenomena. And the discovery of a fast radio burst with the Arecibo telescope, the first telescope other than Parkes, really started to convince people that this must be a genuine astrophysical phenomenon. And it's this particular burst that I'm going to be talking about in most detail during my talk. So really in the last few years or so, since 2015, there's been an explosion of papers, interesting results that are starting to give us the important clues that we need to figure out what this phenomena actually is. This includes things such as the first detection of a burst in real time. So people have been beefing up the amount of computer power that we have at each radio telescope to start detecting this phenomena in real time, because if you can detect it in real time, you can start triggering other telescopes. You can take data of higher quality. You can store, for instance, the full Stokes parameters of the signal. So this first real-time burst also detected circular polarization in the burst, which is interesting. Later that year, there was a burst detected with a very large rotation measure, which is essentially measuring the line of sight magnetic field, and it showed that whatever the site of production was, it must be strongly magnetized, so that was also very physically diagnostic. Another event was found only about a year ago that was equally as bright to the Lorimer burst, suggesting that actually we don't need particularly large radio telescopes. As long as we have a very large field of view, the luminosity distribution may be such that we can actually find a lot of these even with small telescopes. But most of the talk I'm going to be talking about these papers in which the Arecibo fast radio burst that we discovered a few years ago was found to be repeating. So going back to the source, we were able to find bursts at the same dispersion measure and thus the same distance and the consistent sky location. And because the source was repeating, this allowed us to sit on the source for a very long time with every telescope that you can imagine and to start learning more about its nature. And that's what I'm going to talk about in more detail in this talk. So we have this fast radio burst whose name is FRB 121102 because the first burst that was detected on the 2nd of November 2012. And again, it was found with the Arecibo radio telescope in Puerto Rico. And Arecibo's most important operational parameter, I think, in this respect is the fact that it's a huge radio dish. It's 300 meters across. And compared to the Parkes telescope, even though we're sacrificing quite an enormous amount of field of view, the sensitivity is over an order of magnitude larger than Parkes. So it's possible to see much weaker astrophysical signals than with the Parkes telescope. The signal was found in the PALFA survey. This is a survey for radio pulsars in the galactic plane. It's using a 7-beam receiver system, which is basically a clone of the Parkes multi-beam system. And it's one of the deepest surveys before the square kilometer array will come online. And what I think is kind of funny about this is if you make a diagram looking down on the galactic plane, you can see these black lines showing the various spiral arms of the Milky Way. All of these blue dots are showing you discoveries of pulsars and rotating radio transients from the survey. And you can see that Arecibo can see in two small quadrants of the galactic plane. This is because the telescope, the dish cannot move, so it's a pseudo-transit instrument. And you can see that in the inner galaxy, there have been many pulsars that have been discovered, even out to the edge of the galaxy. But in the galactic anticenter region, where there's not that much galaxy to look through anymore, there have been very few discoveries. And you might ask yourself, well, why are you spending time finding a small handful of pulsars in the galactic anticenter? And I was kind of wondering that as well. But the important thing is these data are taken commensally. So there are people using the data for other scientific endeavors, such as looking for extragalactic sources and galactic hydrogen absorption. And even though there have been only a few pulsar discoveries in that direction, the data is coming for free. But quite fortunately, that commensal data is the data in which this fast radio burst was found. So looking at this anticenter region turned out to be useful because that large on-sky time was the reason why we were able to find this burst. So again, this is the burst itself. This is found about three years ago by Laura Spittler, searching through the Arecibo data, specifically looking for fast radio bursts. And this is what she found. This is, again, as a function of frequency and time. The signal has not been de-dispersed, so this sweep that you see is still due to the ionized material between us and the source. If you sum all of the frequency channels together with the appropriate correction, then that's the burst. Not nearly as bright as the Lorimer burst, as you can see. But what was particularly strange about this, and what had a number of us very worried, is if you look at the spectrum of this of this burst is really quite strange. It's obviously becoming much brighter towards higher frequencies. It appears to have an inverted spectrum, actually with a spectral index of +7 or so. And that doesn't seem very astrophysical. That was a little bit strange. In fact, our conclusion at the time is that we must have seen the burst through a side lobe of the telescope where the instrumental response of the telescope was the main driving factor for this spectrum. So the source was in the galactic anticenter. Of course, you know, the first thing you do when you find a source that has a large dispersion measure is you try and figure out whether it could still be consistent with the galactic dispersive column. That's the position of the burst there. There was nothing obviously along that line of sight that could contribute to the large dispersive delay here. And in fact, the dispersion delay for this burst is 3 times larger than what could be explained by our galaxy, depending on, you know, your exact model for our galaxy. But still, it seemed like it must be extragalactic. Now, where the story became much more interesting, however, was when we realized, well, we should go back to the source and we should establish that it's not producing repeat bursts. Even though it's well known within the field that fast radio bursts don't repeat, it's still due diligence to go back and to establish that fact empirically. So we were quite surprised, actually, when we went back and with a short campaign, a campaign of only about 10 hours or so, we were able to detect 10 additional bursts at consistent sky positions. They're all coming from the same direction, and they all had the same dispersion measure. So these are the next 10 bursts. The original burst is at the top there. Here, the dispersive delay has been corrected. So these frequency time diagrams, that dispersive delay has been taken out to try and make you know, this straight as a function of frequency. As you can see, some of the new bursts are much brighter than the original one that was discovered. And also, quite importantly, and I'll come back to this later in the talk, the spectra are highly variable. Some of these bursts, well, the last 6 or so were detected in a time window of only about 10 minutes. And sometimes we're seeing apparent spectra of, you know, -7 and sometimes +10 within a few minutes of each other. So the spectrum is all over the map, and I'll discuss that a little bit later as well. But the most important thing is simply the fact that it's repeating. And this was the first time that we had seen a repeating fast radio burst. And this is a very easy paper to write. You know, what is the consequence of the fact that it repeats? Well, quite simply, the consequence is that the origin of the burst cannot be a one-time only explosion, as was previously popular for FRBs in general. But at least for this particular fast radio burst source, which of course could be different in nature than the other sources, for this particular source at least, whatever is producing the burst has to be able to survive, you know, the production of the bursts themselves. It has to be able to live long enough to produce multiple bursts. So this starts to push more towards models that invoke neutron stars, some kind of pulsar on steroids kind of model. Of course, this also raises the question, you know, if repeat bursts have not been seen from the other fast radio bursts, could it be that we're already seeing multiple populations? And that could well be. It could be that there are fast radio bursts which can repeat that are non-cataclysmic in nature, and it could be that the rest of the population that we've seen thus far could still have a cataclysmic origin. Now, there have been very deep follow-ups of a number of the park's FRBs for tens of hours, in some cases even a couple hundred hours or so. But, well, if you want to discuss this in more detail, I'll take questions on this. There are still ways in which it's possible for these sources to repeat as well. It's just that we have not observed them to do so. And of course, if you look at the archive and you ask the question how many types of fast radio bursts are, there must be at least 40 or so, given all the papers out there. So Arecibo has this multi-beam receiver. This is what it looks like. And the problem is this multi-beam receiver is nice for increasing the field of view, but in terms of localizing the source, it's still quite poor, even though Arecibo is quite large. So all of these different circles, these are different areas on the sky where the main lobe of the telescope was pointed in our confirmation or in our follow-up campaign. And the circles that are marked with numbers there, those are where we found bursts. So the first burst was found in that circle with the 1 in the middle. Ironically, the first burst was indeed found in the side lobe of the telescope because the rest of the bursts that we found were somewhat off from that position, but consistent with the position that overlaps between those other 2 circles. So we're starting to narrow down the position of the source a little bit, but each one of these circles is 3 arc minutes across, and 3 arc minutes just does not cut it for multi-wavelength follow-up. So I'm going to tell you about 3 papers in which we've managed to localize the source and establish its extragalactic origin. These are papers that came out in January, all on the same day. So first, tell you a little bit about how the source was localized. And again, this is critical for assessing its nature. And just to motivate why it's critical, the Arecibo beam is quite small. 3 arc minutes is fairly small for a radio telescope, but it's not an interferometer. And if you do this toy comparison of sticking the Hubble deep field within that field of view, that's how large it is, roughly speaking. So if you ask yourself the question, is this source extragalactic? And if so, which of the galaxies is producing the burst? Well, you have a big problem because there's a lot of galaxies within 3 arc minutes. Now, if you can get localization with an interferometer like the VLA, where the dishes are spread over tens of kilometers, then you can really unambiguously figure out which galaxy produced the source. That was the game that we were trying to play here. So this was quite a challenging campaign, both technically and in terms of patience. Technically challenging because you need to sample at a much higher rate than typically one does with a radio interferometer. You need to sample at milliseconds instead of seconds. And this is a radio image of this field taken by summing many tens of hours of VLA data. So this is one of the deepest images I think the EVLA has ever made. And in this map, you can see a couple radio galaxies, these very bright sources. You can see the positions of the Arecibo beams in which we had found radio bursts, and you can see a number of radio sources in there. Now, this is an image made by sampling the data at tens of seconds, and this is a continuum image. We still have no idea if any of these sources has anything to do with this source of fast radio burst. But by dumping the correlator at 5 millisecond time resolution, Casey Law and Shami Chatterjee were able to localize one of these bursts. So after many tens of hours of observing in which nothing was seen, no bursts from the source were seen for many tens of hours, the source became quite active last fall in September or so. And this is one of the bursts that was detected. And this image now, the reason you only see this one source is because this is a snapshot of only 5 milliseconds. So it's a 5 millisecond snapshot of data. And in those 5 milliseconds, there's a bright burst right there. Now, the star pattern, this is just the response of the telescope, this Y shape of the VLA, the fact that the UV coverage during 5 milliseconds is quite limited. And there it is. Source is localized, and it's localized to less than an arc second. So once you deconvolve, that's what the source looks like. And if you look at it in the frequency time domain, you see that this source nicely follows exactly the dispersive sweep you would expect, the same dispersion measure for this source as all of the other bursts that we've seen. So this really nails the association with the previously observed bursts unambiguously. And what's there? Well, now we can draw a box around the position of where the burst came from, and we can see what else is there. We see that the burst is associated with a persistent radio source. So we've moved back to this continuum radio map now. So that's the radio source there. And in very deep Keck observations, there's also a very, very faint optical smudge there. Not so obvious a priori whether it's a star or a galaxy, because it almost looks like a point source, ever so slightly extended. And I would just like to emphasize that this is a direct localization. The burst was observed in real time with an interferometer, and its position was determined to sub-arc second precision. The other game that you can try and play is you can look after a fast radio burst has happened to see if there's some kind of afterglow. Of course, this has been enormously profitable in the gamma ray burst world. But this is a direct localization, and it doesn't suffer from the same kind of statistical problems that you have with associating different events. How am I doing for time? 7 minutes. Okay. I'm going to have to be a bit faster. Okay. So we have this sub-arc second localization. What's the next thing we want to do? Well, we actually want to determine the position even more precisely. We want to do much better than just arc second precision. And the reason we want to zoom in further is we want to see, do these bursts come exactly from that position of that persistent radio source, really exactly? If so, we want to start understanding their physical relation. And we also want to know, do the bursts come from, let's say that optical source is a host galaxy, do the bursts come from the center of that host galaxy, or do they come from the outskirts? We did this using the European VLBI network, which is a network of radio telescopes spread across the world, including also in Russia, of course, and including Arecibo as well. All of those data are correlated in Dwingelo in the Netherlands, which is a very, very small place with a lot of data coming into it. So we did joint observations using Arecibo, not only because this gives a very long baseline, a very large separation between telescopes, which gives the necessary angular resolution, but also because Arecibo provides the raw collecting area that one needs to detect weak bursts. So during this period of high activity in September of last year, we were very lucky to collect a number of bursts with the European VLBI network. This is the brightest burst as seen by Arecibo. This is an image of it. That's a dirty image, and after it's cleaned, because of the limited UV coverage, one needs to consider what the systematic error is on the positions. We also made some observations of a known pulsar to kind of quantify how the positional accuracy depends on the signal to noise of a burst. And lo and behold, we have a number of weak bursts and one very bright burst that are detected by these telescopes, and we're able to actually localize the source of the burst to be within at least 10 milliarc seconds now, from the position of this persistent radio source. And we've also established that this persistent radio source is compact. We're not even resolving it, or we're ever so slightly resolving it on VLBI length scales, and that resolved nature we think is actually due to angular broadening of the source. So the bursts are coming really from exactly the position of this persistent radio source. So there's a direct physical relationship, I would argue, between the source of the burst and the source of this persistent radio source. Now the real clincher, the last thing that you need to do is you need to figure out what that optical source is. Is it really a galaxy? And if it is a galaxy, what is its redshift? So we did this using the Gemini telescope. This is work that was led by Kees Bassa and Sriharsh Tendulkar. So starting with this Keck optical image, we know that there's this faint smudge there. It's only 25th magnitude, so that's really quite weak. It seems to be slightly extended, but only ever so slightly. It's a very wimpy source. So this means that there wasn't a great deal of enthusiasm about the prospects of getting a redshift for this source, but we were quite surprised. And the reason it turned out to actually be quite easy is because this source happens to be a dwarf galaxy in which most of light is coming through spectral lines. So this is spectrum of what we now know is the host galaxy. In the blue are the spectral lines. You can see H alpha there. You can see a number of oxygen 3 lines, H beta as well. Very weak continuum, so that means that there's actually very, very few stars in the galaxy. And most importantly, what's the redshift? Well, the redshift is 0.19, which implies a luminosity distance of about a gigaparsec or so. And now finally, not only establishes conclusively the extragalactic origin of the source, it also sets the energy scale because we now know the exact distance. And it turns out the peak luminosity of these bursts is about 10 to the 40 ergs per second or so. So this was very important because for at least this fast radio burst, we've now established conclusively, not just using the dispersion measure of the burst, but really finding the host galaxy and its redshift, that the source has to be extragalactic, and we know what distance. We can look at the position of the source compared to the core of the galaxy. This is a very, very wimpy little dwarf galaxy at a gigaparsec or so. You can see the Gemini images in various bands there. The centroids are shown by those crosses, and the position from VLBI is shown there by the other cross. So there's an offset by about 0.2 arc seconds from the center of the galaxy. So it's not right in the center of its host galaxy. And in the last few minutes, I'm going to explain, what this might be telling us. So we know that the host galaxy is a star-forming dwarf galaxy. It's about 1,000 times less massive than the Milky Way. So you can see the Milky Way there for comparison, and the host galaxy is that little green smudge there. And one of the reasons this is interesting is because such galaxies are actually known to be preferentially the hosts of long gamma ray bursts and superluminous supernovae. So it's really quite intriguing that the first fast radio burst that we've been able to localize to a host galaxy happens to be in this peculiar type of host galaxy that also hosts long gamma ray bursts and superluminous supernovae. It certainly at least gives the tantalizing prospect that maybe long gamma ray bursts and superluminous supernovae are the types of explosions that produce the progenitors, the engines that create fast radio bursts. So you could imagine, for instance, long gamma ray bursts or superluminous supernovae producing, for instance, in one of the models that's out there, some kind of millisecond magnetar, which is quite young, maybe only tens of years, and through the decay of its magnetic field is producing fast radio bursts. This is one of the possibilities that seems promising, at least. So what have we been able to do in the last few months or so? Well, quite importantly, this is work by Kees Bosse in the Netherlands. Kees got, in collaboration with Sriharsh Tendulkar at McGill, he got a nice Hubble image of the host galaxy, so this gives us better angular resolution than we were able to achieve with Gemini. So you can see in the oval here, this is the extent of the host galaxy, the very weak star formation from this very small galaxy. But we see this very, very bright knot of star formation. That's where all of those spectral lines I was showing you in the Gemini spectrum are coming from. And again, the VLBI position of the fast radio burst is shown by the little X there. We see that the fast radio burst source is associated with the star-forming region. It's ever so slightly offset from the centroid of that star-forming region, but it appears to be physically related to that star-forming region. So, of course, that's another interesting clue because it suggests that whatever the source of the burst is, it's a young object produced in a star-forming region. Unfortunately, we haven't been able to find anything in X-rays. There is no persistent X-ray source. So that's the position of the burst there, and this is a Chandra image in which there are just two little lonely photons in there during long observation. And we have simultaneous radio X-ray coverage that we were able to take with Arecibo and with XMM, which shows also at the time of the burst, at the time of the radio burst, there are no coincident X-ray bursts. But I should give one very important caveat here. The distance to the source is really quite enormous. So even in some of the plausible magnetar models, given the large distance and the size of our current X-ray satellites, you would kind of just barely maybe expect to see some of these X-ray bursts. So I don't think we're able to rule out that there is some kind of simultaneous X-ray burst here. To do that, we would need to find a similar repeating source at much, much smaller distance to be able to probe these ideas, I think. And lastly, during the VLA campaign, we also had simultaneous Arecibo coverage. So we see, in some cases, bursts at two telescopes at the same time in different observing bands. And we see sometimes that the signal is very, very broadband. So in this particular case, we are able to catch a burst from 1.2 to about 3.5 gigahertz or so. So in some cases, the bursts are very broadband. But in other cases, we see that the bursts are very, very strange in their structure. So what's shown on the left is one of the brightest bursts that we've seen with Arecibo to date. This is what we're calling weird bursts. They have a lot of structure to them. So in the top panel, that is the burst structure. So all of those bumps and whatnot are real. But the data has already been de-dispersed in this case. So you can see that there's substructure, that there's sub-pulses to the burst. And they actually are delayed with respect to each other in frequency and time. They seem to drift down to lower frequencies with time. And we don't think this is dispersion. One of my postdocs, Anne Archibald, she was kind enough to print out this particular burst in 3D with her nice 3D printer. So at coffee, if you want something to poke someone with, you can take a look at this. I think it's an easier way of visualizing this than what's shown on the screen there. And we think that this spectrotemporal behavior is going to be highly diagnostic for understanding the environment and or the emission mechanism. So in summary, this particular fast radio burst, 121102, it requires a source that can survive creating the burst because we see repeated bursts, right? It is located, we now know, unambiguously in a galaxy at 1 gigaparsec, so at a redshift of 0.19, and it's in a star-forming region, specifically in that dwarf galaxy. And this is a type of dwarf galaxy where the metallicity is very low. You can form very, very massive or very fast-rotating stars, and where you expect to see long gamma-ray bursts and superluminous supernovae. The source is consistent or coincident with a persistent radio source. I would say it's associated with a persistent radio source given the enormously tight constraint on the angular offset. This could be a nebula. Maybe Pat will jump up and say, how could it be a nebula? Because this particular source would have to be about 500,000 times brighter than the Crab Nebula, so that's challenging. Or it could be AGN-like. There are certainly models out there suggesting maybe if you had a neutron star interacting with an AGN, you could produce such electromagnetic bursts. In any case, if it is a nebula, it needs to really be quite unlike any of the pulsar wind nebulae or magnetar nebulae that we've seen in our own galaxy. The energy scale of the burst is now well established, and I think it's still possible to get this out of a neutron star. Certainly, you know, if you increase the rotation or the magnetic field or the efficiency of the radio production, then you can get the orders of magnitude that you would need. And lastly, I think, you know, the spectral temporal behavior that I just showed you is going to be really interesting, and there are ideas about how we could potentially produce this with lensing of the burst by plasma around the source, or it might be telling us something interesting about cyclotron masers being responsible for the weird spectra that we're seeing in the burst. So thank you very much.
Questions? Please.
Yeah. So we have an ongoing VLBI campaign in which for the next couple of years we're getting about 4 epochs a year in which we're going to measure the position of the source, and we can put further constraints on the proper motion. So if you think that, for instance, that the association with this host galaxy is still questionable, then you can also, from the point of view, look at the proper motion of the source and constrain its distance that way. Yeah.
Sergey?
What's roughly the total number of detected bursts and how they are distributed in time, like coming in first?
Yeah, that's also a very good question. I didn't have time to get into all of the details about the source, but we now have, in a campaign of about 130 hours, we have about 132 bursts now. And many of those bursts happen within a few-week period. So there's definitely a clustering of the bursts in time, and there are periods of tens of hours where we see basically no bursts, and then periods of even an hour where we'll suddenly see 10 or 20 bursts or so. So they're definitely clustered in time.
And what is the luminosity function of the bursts?
That, it's a power law. I think it's 0.7 or so. Yeah, so we're not even seeing the weakest bursts yet, even with Arecibo. Yeah, so unfortunately there's only one Parkes FRB that's far enough north that it can be seen with Arecibo, but we've been following it up. So far we haven't found any bursts. The one that was found with GBT is also being followed up with Arecibo. There are plans with some of the new FRB machines, the telescopes that should find many dozens of these, like ASCAP and also CHIME in Canada. Especially CHIME in Canada is going to be a transit instrument, so it's going to see the same sky every single day, and they're going to find ones, and they will naturally see whether they're repeats or not. Now, for the ones, sorry?
Let's say if you downscale this repeating burst, obviously telescope sensitive enough to see the repeating burst of this one.
Yeah, I think the very brightest ones should be visible still. Yeah, that's right. But because of the varying activity level, I would argue that we don't actually have strong constraints on the Parkes ones yet to know whether they really, it's impossible for them to repeat. Because if the activity level is clustered in time, it becomes more and more difficult to put strong constraints on repeatability.
While the next speaker gets ready, we take another question from Ali.
That's a good question. It's quite small still. It's still much, much smaller than the persistent source by many orders of magnitude. I don't want to give a number because I need to think about it more carefully, but it's still very, very low because even in an observation where you have 2 hours, 20 bursts, this 20 bursts for about, 30 or 40 milliseconds over the course of 7,200 seconds or so. So it's very, very low still, the time averaged.
But
I think there were a couple of them in the end. So I think in total it was about 60 kiloseconds or so. So you'd have to, the prospects for going deeper are not very good, unfortunately. Yeah.
There are other questions? If not, we thank again Jason.